In our last video, we talked about exponential functions and the applications of exponential functions, but we haven't really talked about exponents themselves yet. So in this video, we're going to start talking about the exponential properties, and we're going to prove some of them, and then in the next video, we're going to apply them. Okay, so some of the exponential properties you're going to be really familiar with. We're going to talk about 7 of them. So the first one is the property of multiplication, which says that if you have the same base, and let's actually make sure that you're familiar with the terminology first. So if we have a to the x, okay, the a is the base, and the x would be called the exponent or the power. And the way that we would say this is a to the x, or a raised to the x power. If you that might be helpful if you grew up in a different country and learned about exponents in a different country. So we would say a to the x power. Okay, so some of the exponential properties. The first one is property of multiplication, which says that if you are multiplying and you have the same base, then you can just add the exponents. So a to the x times a to the y is the same thing as a to the x plus y. And not surprisingly, if you are dividing, you have a to the x over a to the y. So same base, but dividing. Then we subtract the exponents. It becomes a to the x minus y. Okay. Then we have distribution. So if inside the parentheses you are multiplying and you're raising that to the x power, you can distribute the exponent. Sorry, that should be, this is not coming out well in terms of the writing, but this is a to the x, b to the x. Okay, so we can distribute the exponent because inside the parentheses we're multiplying, and outside the parentheses we're raising to an exponent. So if you remember from the order of operations video, you can distribute when what is inside the exponent is one operation lower, just one operation lower in the order of operations. So if this were addition in here, you would not be able to distribute because addition and exponents are separated by multiplication in the order of operations. So it's got to be immediately below. Okay, multiplication is immediately below exponents. And just like when we're multiplying inside the parentheses, we can distribute for the same reason. When we divide inside the parentheses, we can distribute because, again, multiplication and division are on the same level. So if multiplication is one operation below exponents in the order of operations, then so is division. So we can say if we have a over b to the x, that is the same thing as a to the x over b to the x. Okay. We can also say that anything raised to the 0 power is 1 So by saying A, we're saying any number that we put in there. So any number raised to the 0 power is 1, except for 0 to the, except if A is equal to 0. So where A is not equal to 0. Okay, and just as a side note, zero to the 0 is undefined. Okay, the reason for this is that if you have 0 to any power is 0. Okay, if you have 0 to any power, 0 to the x is 0. So that could be a 6th property. 0 to any power is 0. So the problem is that when you have 0 to the 0, it satisfies both of these, and you can't have both things being true simultaneously, so we just say it's undefined. So again, we would say where x is not equal to 0. Because you can't have both properties holding. Okay, so then the next property is something raised to the negative power. So a to the negative x is the same thing as 1 over a to the x. And finally, the last one would be if you have a power raised to a power. So a to the x to the y. That's the same thing as a x to the y. So you can multiply powers. Okay. And what we're going to do is we're just going to prove a bunch of these. Okay. So the first proof, we're going to prove that a to the x times a to the y is equal to a to the x plus y. Okay. So what we're going to do is we're going to take each piece of this. We're going to look at the left side, and then we're going to look at the right side and see what it means and show that they're equal to each other. Okay. So let's start with the left side here. And let's just think about the definition of an exponent. So when we do definition of exponents, what we're saying is that a to the x means that we're taking a and we're multiplying it by itself x times. So if we have 2 to the third, then we're doing 2 times 2 times 2 3 times. And if we could say that about a to the x, then we can also say that about a to the y. So this is just saying we're taking a and we're multiplying it by itself y times. And our reason for this, if you remember, in proofs, we like to put in reasons for things. So this would just be considered the definition of exponents. And then we can say, okay, well, let's multiply these. Well, if we multiply these, e to the x times a to the y what we're saying is that's A times A times A, x times A times A times A, y times and this is just x plus y times, right? If we have x a's and y a's, then together it's x plus y. Okay, so this is the left side. But now we have to show that the right side is the same thing. So let's use a light blue for that. So the right side is a to the x plus y. So what is a to the x plus y? Well, again, by definition of exponents, we're saying, well, this is a times a times a times a, and this is x plus y times. And why is that the case? Again, it's just the definition of exponents. And I'm going to abbreviate definition with DEF. Definition of exponents. And this is our right side. So we're looking at the left side, we're looking at the right side, and they're the same. So if they're the same thing, sorry, I'm just charging this pen. Hang on one second. Sorry about that. So if they're the same thing, if the left side is equal to the right side, then they have to be equal. Okay, and this actually has a name. It's called the transitive property. So let's write that down. So we say therefore, this is the sign for therefore. It's 3 dots in a triangle. This is the way that we end every single proof that we do. We're saying, therefore, we did it. Okay, so therefore, a to the x times a to the y is equal to a to the x plus y. Okay, and why is that? Because what we see here, what we see on the left side is the same thing as what we see on the right side. They are both equal to the same thing. Therefore, they are equal to each other. And this has a name. It's called the transitive property. Okay, and you can just use transitive property instead of writing they are both equal to the same thing, therefore they are equal to each other. And just to verify that we're done, this therefore usually verifies it, but in math we do something a little extra. We use something called QED. So QED is a Latin term, it's shorthand for a Latin term that essentially means we did it, we're done, let's celebrate. And it's just, you'll see it at the end of lots and lots of mathematical proofs, just to say, okay, see, I did it, I'm done, that's it. Okay. Okay, so let's do another proof. And all of these proofs are very similar. Okay. So let's prove, the proof for number 2 is very similar. Let's do number 3. Let's do this distribution one. Okay, so we're not going to prove every one of these. We're just going to prove one, and then we're going to assume that the counterpart is very similar, because it is. Instead of doing x plus y, we would be subtracting terms. We'd be doing x minus y, because a's would be canceling. So we don't have to worry about doing it all. And same thing here. The proof for number 3 is very similar to the proof for number 4. So we're only going to do the proof for number 3. Okay. So again, proof. We're going to be doing AB to the x is equal to A to the x, B to the x. Okay. And again, what does this mean? We're going to show that the left side is the same thing as the right side. So let's start with the left side. And we're going to be using the definition. What does AB raised to the x power mean? Well, it's AB times AB times AB. This dot, dot, dot means that there are lots of ABs in between here. We just don't know how many there are because we don't know what x means. So this is x times. Okay, and this is just by definition of exponents. And again, I'm abbreviating definition with DEF. Okay, so now we need to take this a little bit further. Let's rearrange it, because up here we see A first and B second, and we can just rearrange this here too. So we could say, okay, well then what does that mean? That means that AB raised to the x power is the same thing as A times A times A x times B times B times B x times. This is all multiplication. Okay, this is all multiplication, so all we did was just rearrange it. We put all of the A's before all of the B's, and we're allowed to do that. We call that the commutative property. Please note the spelling. Commutative. It's with a T. Some of you may think it's commutative. It's not. It's with a T in there, commutative property. And the commutative property says that we can just change the order of something. So if we have C times D, that's the same thing as D times C. We could switch the order around. Okay, and we're going to say that this is the left side. Okay, let's move to the right side. Okay, and we say we're moving to the right side because there's really nothing else that we can do with this. Once we can't go any further, we move to the right. And it's possible with some proofs, not with this one, that you might go back to the left side because you might discover that, oh, wait, I thought I was done, but I'm not. Okay. So in this one, that's not the case, though. So the right side is saying a to the x, b to the x. So we're going to expand that. And we know that that is saying that we have a times a times a x times and then times, because a to the x times b to the x, b times b times b, x times. And this is due to definition of exponents. All we did was expand. And we can't do anything else here. So now we're done with the right side. And as you can see, the right side is equal to the left side. So we can say, therefore, a times b to the x is equal to a to the x, b to the x, and this is because of the transitive property. Right? They're both equal to the same thing, so they must be equal. And if they're both equal to the same thing and they must be equal, we're done here. So in order to just make it clear that we're done, we're going to say QED. Okay. Transitive property. I can put it in blue. What we're saying is, if C is equal to D and K equals D, so they're both equal to the same thing, then C is equal to K. This is another short way of writing the transitive property. Okay? But again, you don't need to write this. This is just for your reference. Okay, so that's the proof of the distributive property. Now let's go back. This is also the distributive property, so we're not going to prove this. We will prove this, but not now. Okay, we'll do that afterwards. And same thing with number 7. We'll prove number 7, but let's jump to number 8 first. Okay. So a proof a to the x to the y is equal to a to the x y. And we're going to approach it in the same way. Left side versus right side. So left side first. So a to the x is equal to a times a, and so forth, times a, x times. So we're taking this inside part here. And we already know that this is just definition of exponents. Okay, so we looked at the inside part. Now we're going to add in the outside part. So we're going to do a to the x to the y. So this is equal to a to the x times a to the x times a to the x y times. And again, this is just definition of exponents. Okay, well now we can keep going with this because we know what a to the x is, right? A to the x is just this, a times a times a x times. So I'll write this again, a to the x to the y is really just a times a times a x times times, again, a times a times a x times. Each of these is equivalent to a to the x, right? X times. And again, we have a times a times a x times. And how many times is this happening? It's happening y times. Okay, well, what is this? So this is just substitution. That's the reason for this. We just substituted. Okay, well, we can rewrite this one more time. That means that a to the x to the y is equal to a times a times a x times y times. And the reason that we can say that is that here we have y groups of x, okay? This is happening y times. So we have x plus we have another x plus we have another x and we have y of these. So how many do we have? X times y. If we had 2 cookies and then we had another group of 2 cookies and then another group of 2 cookies, then we have 3 groups of 2, so we can just do 3 times 2. And that's multiplication, okay? We have y groups of x, and that's the definition of multiplication. Okay. This is the left side. So now we just have the right side. Well, a to the xy, we know is just a times a times a x times y times. This is the definition of exponents. It's the right side. Therefore, the right side is equal to the left side. So therefore, a to the x to the y is equal to a to the x y. This is the transitive property. I'll leave that in red. And we would just say QED. We're done. Once we prove that the left side equals the right side, we're finished. Okay, so 2 more quick proofs. Let's prove that anything to the 0 power is 1. Okay, well, this is a little bit different because we're not going to use the transitive property because a to the 0 is just one thing. So there's no way to expand it. There's nothing that we can do here. But what we can do is we can use a property that we already know. So we're going to use this property of multiplication here. That's number 1. And we can do that because we already proved it. And once we prove something, we can use it in all future proofs. So we're going to use a to the x times a to the y is equal to a to the x plus y. And when we use this, we're going to say, okay, well, let's let y equal to 0. So a to the x times a to the 0 is the same thing as a to the x plus 0. And we already know that a to the x plus 0, well, x plus 0 is x. E to the x times a to the 0 is equal to a to the x. Okay, well, this is the identity property of multiplication. This right here. And this is the key step. Identity property of multiplication says anything times itself is equal to, anything times 1 is equal to itself. So here we have something I'm just trying to make this clear. Okay, we have something times a to the 0 is equal to itself. That means that a to the 0 must equal 1. Okay, because we already know anything times itself, anything times 1 must equal itself. And we have something equal to itself. So a to the 0 must be 1. right? This is the identity property of multiplication, that anything times 1 is equal to itself. So therefore, a to the 0 is equal to 1. That's the identity property of multiplication. There's nothing else to say here. QED, we're done. Now we're going to do something very similar for the next one. Just think about what we did here. We said, okay, well, we know this rule. So in this rule, let's assume that y equals 0. We're allowed to do that. We can say let anything be anything as long as we don't break any rules. If we assume that y equals 0 and we apply it to this rule, then a to the x times a to the 0 is the same thing as a to the x plus 0. If you have the same base, you add the exponents. But x plus 0 we know is just x. So we have a to the x times a to the 0 equals a to the x. Identity property of multiplication says anything times 1 is equal to itself. So therefore, a to the 0 has to be 1. Otherwise, this could not be the case. Okay? And I'm just going to, some of these letters didn't come out for some reason. They still didn't come out. I'm going to try erasing it. Sorry, it's coming out on what I'm writing on. It's just not coming out here for some reason. So I'm going to try writing it above. Still didn't work. That made it worse. I'm going to put it elsewhere. I'm going to put it down here. Okay, that's better. So we're going to use something similar to prove the last rule. And there are sometimes more than one way to prove a property. So if you were to look this up, you might see another way to do it. Okay. So the last proof that we're going to do is that if we raise something to a negative power, that's equal to 1 over that same base raised to a positive power. So if we have, for example, 3 to the negative 2, then that's the same thing as 1 over 3 squared. Okay, so I'm going to put that just off to the side here. 3 to the negative 2 is the same thing as 1 over 3 squared. Okay, b to the negative 5 is the same thing as 1 over b to the 5th, just so that you can see how it works. So again, we're going to use something that we already proved. We're going to use the same property, okay? And the only difference is that we're going to let y equal negative x. Notice we let y equal 0. Here we're going to do the same thing, except we're going to use this exponent. So let's write that down. A to the x times a to the y is equal to a to the x plus y. And this time, we're going to let our y equal negative x. Okay, well, what does that mean? That means that now a to the x times a to the negative x is equal to ax plus negative x. Okay, well, we know that x plus negative x is 0. So we're just rewriting here. And a to the 0 we know is equal to 1. We know that because we just proved it. So what does that mean? A to the x times a to the negative x is equal to 1. Okay, well that means that a to the negative x must be 1 over a to the x. Why is that true? It's the inverse property of multiplication. Instead of the identity property, it's the inverse property of multiplication. Okay, the inverse property says anything times its reciprocal equals 1. So, for example, 3 times 1 over 3 is equal to 1. 6 times 1 over 6 is equal to 1. So we can say, therefore, a to the negative x has to equal 1 over a to the x. Because otherwise the inverse property of multiplication wouldn't hold, right? If a to the negative x were anything else, this could not equal 1. So we're done. So we proved all of those properties of multiplication. Again, all of those properties of exponents. Again, sometimes you might see different proofs for these. I'm only going to show you these, but feel free to look online and you'll find others. Okay, and in the next video, we will apply the properties of exponents.